we can extract those things, but the other thing is that it's very hard to do this integral exactly, and so we are not doing it. We are just writing it in this form. Okay, we are just going to evaluate this integral in various limits. Okay. Now let's look at, let's see if how our familiar equation of state, for example, in a classical limit, you'd expect PV equals to nRT to emerge from this, right? How does that emerge from this, right? So let's look at that. But
So
before we do
PV
that,
is
yeah.
equal to 2 by 3 integration. How does this line emerge?
Oh, this is the definition of the. So this is the density of state, right? This is the density of state. 1 over this is the Bose-Einstein statistics, which is the probability function, and this is E. So that this whole thing is just the definition of the expectation value of E.
Sir, but how is that equal to PV? I am confused on that.
Oh, you're right. So previously we had said PV is equal to this, and we have just evaluated this thing to be this thing. And PV was equal to that because remember that if Z is the grand canonical partition function or a grand partition function, the nice thing about the grand partition function is that when you take its log, it's going to be proportional to PV, right? That's something we did, the grand potential.
Yes, sir.
Okay. So this is what we have. So let's, we just wrote down a formula. It doesn't really mean much at this point. So now note that E is a function of mu and T, right? So to express this equation in the usual form, we will need to evaluate what n is. So what is n? N is just nothing but the number of particles. So it's just the integral of the density of states given by times the times this thing, the Bose-Einstein statistics. So again, this is a difficult integral to do, but what I want you to notice is not that. I want you to notice is that n is now a function of mu and t. So suppose that we have done this integral. Once we have done this integral, we can invert this equation and find mu as a function of n and t. And once we have done that, we go to the expression for E, which is a function of mu and t, and then we plug in this mu as a function of n of t, and then we get some expression for E as a function of n and t. Okay, so once we have done all of that, so if we have done this integration and then invert this, and then we go back and eliminate mu from this expression, it's only then that we will get PV is equal to some expression for E in terms of n and t. Okay, so that is so instead of doing that exactly, let's see how we can do stuff in the limit of high temperature and low temperature. Okay.
Sir, why are we excluding the dependency of mu?
Yeah, that's a very good question. It's just that mu is, the reason why we introduced mu in the first place was because deriving Bose-Einstein statistics and the Fermi-Dirac statistics for a fixed number of particles was difficult, because the sum that we had to do had to be constrained, and doing constrained sums are difficult. And that's why what we did is that we chose to do unconstrained sums, but the price that we had to pay is that we kept the number of particles arbitrary, and therefore we had to work in the grand canonical ensemble, where the mu appears explicitly. So now the thing is that in many cases, you actually want to fix the number of n, and you don't want, so you're not interested in mu. So in those cases, you want to have an expression where mu is absent. That's why you want to so that's what we are interested in. We are interested in physical applications. We're interested in the case where the number of particle is fixed. Because at we are not doing relativistic physics, where in relativistic physics the number of particles can change, and that's why we have quantum field theory. But in quantum mechanics, the number of particles remain unchanged unless there is a chemical potential, which means that their particle being injected into the system or being taken out of the system. But in everyday situation, if you're looking at, suppose we are studying the Bose-Einstein condensation of a given amount of fluid or a gas, we are not expecting new particles to appear out of nowhere or particles to disappear. So we are looking for n to be fixed, and therefore we don't need mu to be there. Okay?
Okay.
All right. So, no, that's a very good question, and this is basically the price that we have to pay for having worked in the grand canonical ensemble. This sort of gymnastics that we have to do.